times 1 over log n to log n. So that's even less than fundamental. This is less than 1. Right? So these are just calculations. Okay. So I know this might not be like this super impressive result here, but my main idea here is to just show you some techniques that might be used elsewhere. So what you have to take from here is that we make some random choices and then reduce some hard problem to some easier ones. And actually, this can be brought further. We can actually solve the problem for k being equal roughly to log n. And the algorithm is not much more difficult than this one, but this one again is a research paper from I think 90s. It was a pretty big theoretical result, and since it uses this technique and it's quite easy, I'm going to show it to you. So the technique is called color coding. So we start with a different approach. Let's say we have a graph again, and we want to check if there is a path of length k. And for that, we use dynamic programming over bit masks. So in order to find a long path, we can do the dynamic programming over a subset of vertices. That's a vertex P, and this means, is there a path, a simple path, that uses vertices from set S and in V. Okay. This array, this has 2 to the n possible values here, so because we take any possible subset of vertices, we have n possible values here, so we got like O to 2 to the n times n states, and we can fill this array with dynamic programming, and then this would give us the answer for the question: is there a path basically any length, right? We assume that this path is using all vertices from a set S, so basically in the end we'll have to find the biggest set S for which we have some value of true here, right? Like the biggest set S which is completely used by some path. Right, so this gives us, as I said, 2 to the n times n, but we can use our technique to speed it up significantly. So what we'll do, we'll first color vertices randomly with k colors, and then we're going to search for a colorful path of k vertices. Colorful means that every vertex on this path is a different color. So what I want to have is something like that. There's a path, every vertex has some color, and every color on this path is different. So my algorithm would not find paths on which some two colors repeat. I'm only going to find those. So given a graph with colored vertices, how do I search for a colorful path of k vertices? Well, I can do a very similar approach, like here. So I use dynamic programming, but now the bit mask is over a set of colors. So this is a subset of colors that I've used. And this is the last vertex. So it's like, is there a path, a colorful path that uses exactly colors of C and ends in E. Okay, is it? Can you see how to fill this array with, like how to proceed with this dynamic programming? Okay, so we can fill this array and find all colorful paths in our graph. I mean, we can find the longest colorful path in our graph. And the running time of it is, well, this has like 2 to the k stays here times n stays here times, I guess, something like n for filling in the array. So we got 2 to the k times n squared time. So the last question that we have to ask ourselves is, okay, we've simplified the problem, we got a colorful version, but what is the probability that the simplification was correct? So in other words, what is the probability that once we fix a path, path P of k vertices, what is the probability of P becoming colorful? Yes?
Still reach no problem.
We still want to find the longest path.
Longest.
Yeah, longest path. So this was the solution for that run in 2 to the n. We consider like every subset of vertices, and we check if there is a path of that gives us exactly the subset that's somewhere. And now we're transforming it to the colorful version. So I'm assigning random colors to the vertices, and now I want to check if there is a path of k vertices that has on which every 2 colors are different, right? And I can do that with this dynamic programming. So the question now is, what is the probability that when I color a path of length k with k the colors, what is the probability of the path becoming colorful? So how many colorings are there in total, like on what path? Yeah, so there are k to the k possible colorings. So for every of the k vertices, I can assign any of the k colors, and out of these, there are k factorial assignments of distinct colors to the vertices, right? I mean, the colors can be assigned in any order. This is number of root colorings. Number of all colorings. So this is the probability of this path surviving our simplification step, and we have this probability, and we can show that, well, as I wrote before, this is something like k over e to k over e over k, k. So this is, I think, I think it's just I know the result, but find that one. Okay, let's see, wait. So it's k over e times e k over e over k k. And I want to have, and I want it to be big, so it's smaller than. Oh, sorry. Okay, I got stuck. Can you help me out with this one? I think it's, so the result is it's bigger than 1 over, that's what I want to get. Like I said, I'm really bad at doing calculations on the board. Okay, I don't think it's very smart to perform some bad calculations, so let's just, I mean, this part holds, and I don't think we have to do the math exactly here. So the point is that we have this probability of the path P becoming colorful, and this is also the probability of our one step of algorithm being correct. And this means that we repeat this process like e to the k times, and get, what do we get? We get e to the k times 2 to the k n squared, which is 2e to the power k n squared algorithm that has a decent probability of being correct. So if k is like the logarithm of n, what we get here is a polynomial, and this way we can identify a path of find a path of k vertices if one exists. And maybe the last example now we'll do as an exercise for you. So this is maximum magic in general graphs. So we have a graph. And we want to find the maximum set edges with distinct endpoints. In other words, in a graph, we want to connect as many vertices as possible in curves using edges, right? So a sample matching would be something like this. Right? You want to find the biggest set of edges so that those two edges have a common endpoint. And this problem has a polynomial solution, but the problem with the solution is that it's quite hard. And what I want you to do now is try to think of a solution which might have some very, very bad runtime, but it's much easier to be understood and also easier to code. So yeah, the task is to find a matching in a graph. And let's have maybe 5 minutes for that. So maybe a good question to ask here is, what is a simple variant of this problem that we might use for solving it? Like usually it's like, think of a simple problem that you're able to solve and try to get from one to the other. Yeah,
maybe deleting some edges, so you eliminate both cycles.
Okay, so what you're saying is that so since we can solve the problem in a bipartite graph, so a bipartite matching is a common problem that's much easier than this one. Let's try to make this graph bipartite by making some random choices. Okay, that's a good start way to go. And the question now is how to do that.
And randomly split the vertices into two sets.
Mm-hmm.
Then only maintain the edges that join vertices from different sets.
Yeah, exactly. That's the way to go. So what we do here is we randomly, well, set split, I'll say color, so that I'm consistent with what we did before. So we randomly color the vertices with 2 colors. So basically, for every vertex, we toss a coin and say that it's black or white, depending on the result. And then we remove edges whose both endpoints have the same color. So after that, we get a graph in which vertices have colors and every edge has endpoints of 2 distinct colors. And such a graph is clearly a bipartite one. You get a bipartite graph. Maybe G prime. And then third step is, since this is bipartite, we can find maximum matching in G prime and hope that it's also the maximum matching in the original graph. So as before, we need to bound the probability of our solution being correct. And what we have to do is that we have to fix some matching, fix some max matching in the original graph G, and we have to bound the probability of this matching being also present in this graph. So what is the probability that this matching survives the second stage? When this happens, what has to happen?
For each edge, you have to forward the 2 vertices with 2 different points.
Yes, that's right. So every edge of M has to be colored with distinct colors, with 2 colors. So this happens with probability, 1/2 per edge, or 1/2 the size of M in total. That's the probability that the matching, the endpoints of every edge for the matching have distinct colors, so this matching survives this second phase. And once we do that, we can find max matching in G prime, and so the last step takes something like say n times m. We can do it a bit faster, but that's with the simplest approach possible. So since this is as before, this is the probability of the algorithm being correct in one trial. So we repeat hundreds is very a lot. Practice 30 times 2 to the size of m. And the size of m is, well, size of m is at most n/2, right? Every edge of the matching eats 2 vertices, so there can be at most that many. So it's like 30 times 2 to n/2, and this gives us an algorithm running at 2 to n/2 times n times n time, which is cool because, like, I think if you want to solve this problem somehow, you might think, okay, let's maybe use some dynamic programming with bit masks, and then we have 2 to the power of n here, times something. So the simplest solution with bit masks maybe works for, I don't know, 20 vertices or 20 something. And I think here you'll probably be able to get to solving the problem for a graph with maybe 40 vertices. And again, this analysis is for the very unlucky case that the graph is just a single maximum matching. If this this graph has more maximum matching, so our probabilities are higher, and we're gonna find a solution faster. Okay, before the break, I'd like to show you one more thing, which is from a slightly different area. So this was all a random simplification technique, and although we were dealing with problems with pretty high running time, I think this can be used in many places, and I think it shows a nice way of, yes?
Could you use of this algorithm if there's a, you can use like a code that's small and is into you?
Yeah, so, well, there are two. Like, one is that I believe this is like conceptually simpler, and two, it's to illustrate the technique.
Oh, just,
Like it was an exercise, right?
oh, okay.
So, it's not that I from now on start using this one and like throw away all the other ones. It's like this was more like an exercise. Right. So this was randomized simplification, and so again to recap, it's a technique that allows you to solve some problems which are seem quite hard in the very beginning. And the approach you take is, okay, I have this problem, so let's think of a simpler variant of the problem and try to randomly get from one instance to the simple instance and try and solve the simple one. Then you have to bound the probability that you got and repeat the algorithm sufficiently many times to amplify the probability. Now in the remaining part of the lecture, I'm going to show you an example of a different randomized algorithm, and this is not connected to the first one, but I think it has a particularly beautiful and unexpected solution. So, okay, different topic. So if you fall asleep during the first one, the first part, now it's time to wake up because we're starting something new. We'll consider a graph problem here. It's a task that was in some contest we organized some time ago. So the problem is about dealing with dynamic graph, a graph that's changing over time. So we have input, we have a graph G. Can you see this from the back? Okay, I'll switch to black then. Fine. The problem is like we have a graph that's changing all the time, and so we have operations like add or remove an edge, and we have a query which is like given a set of vertices, check if this set, if there is any edge going through the boundary of the set. So if there is an edge that has one endpoint in the set and the other outside. In other words, check if this set contains entire connected components. This set does not cut any connected components into two parts. So we have a graph G, and the goal is to process operations. The operations are add or remove an edge, from U to V. It's one type of operation. And the second one is given a set S of vertices, check if there is edge with only one, exactly one endpoint in S. Is it clear? Okay. So once we see a problem like that, we try to think of some clever data structure that allows us to list edges very quickly. So we'd like to have, for some vertices in S, each of those vertices has some edges. And for every vertex, we'd like to be able to say, well, you have some edges, and is this true that you have some edge that's not inside set S? But many people have tried, and I don't really know of any approach that works with that. I mean, this is the most natural way of thinking, but it does not help at all. And what you can do instead is to try to do something totally different. So what do we do? First, for every edge that we have, we need initially for the edges that we have at the beginning, and then for every edge that we add, draw a random number, say 32-bit number maybe, for every edge from U to W, a random number, say A, U, W. Now, after that, the edges have some numbers. For every vertex, U, maintain a value, and that's the tricky part. Let's say it's SU, which is equal to the XOR, let's denote XOR by this symbol, of all values A, U, V for all edges, UV is an edge, incident to U. So for a vertex, we have some number A, U, V1, A, U, V2, A, U, V3, A, U, V4, and we simply XOR these values and maintain it here. And this is all the information that our algorithm is going to maintain. So observe that it's very easy to compute this in the beginning. We just draw the numbers, and then in every vertex we go through all edges and XOR some numbers. Nothing's happening here. And also, if an edge is added, we add the edge, and we have to update to values and vertices. If an edge is removed, what can we do when the edge is removed? Yeah, the same thing, right? Because if this thing has some value XORed, then if we XOR it again, these two numbers will cancel out, and we can maintain. So those numbers are all we need to know about the graph. Now, how to process a query? They have a query about a set of vertices. What we do to check if there is any edge leaving it, we XOR all the numbers in the set. What happens now? So if we XOR the values SU for all these vertices, then for each edge like this, well, in the end, we'll XOR the number A, U, V, well, once here, and then the second time here, right? So these things will cancel out. Now for every edge which is leaving the set, we'll XOR this number here, but we're not going to XOR it again. So if we XOR the values for all vertices in a set, what we obtain is a XOR of the numbers on the edges leaving the set. So since these were random numbers, random 32-bit numbers, we got, as a result, if there are some edges leaving the set, what we get is a XOR of some random 32-bit numbers. And we'll have to be really unlucky to get this XOR equal to 0. Of course, if there is at least one edge leaving the set. Of course, if there is no edge leaving the set, then the XOR is equal to 0, and we claim that there is no edge leaving S. So the algorithm is like XOR the numbers inside. If the XOR is equal to 0, then this is probably a closed set, a set with no edges leaving it. And otherwise, if the XOR is non-zero, we are sure that there is some edge leaving the set. Okay, clear? Great. Okay, so that would be more or less it for today's lecture. We'll have a break in a second, but before that, I'd like to make a very like a 2 or 3 minute introduction to tomorrow's lecture. Tomorrow's lecture would be basically an analysis of some pretty complex problem. It's a problem candies from BOI, Multiplicative Informatics 2010. Does anyone of you know it?
I think so, I'm not sure.
Oh, you think so? So then let me recall the problem. So the problem is like we have n boxes of candies, and the ith box contains AI with 7,000 candies. The question is, so, and then the customer comes and asks for M candies, and the shopkeeper goes. The shopkeeper, in order to serve this order, has to bring boxes such that the total number of candies is exactly M. Now, what we might do for this set of boxes of candies is to check how many different orders can be served. So, is it possible to obtain a sum of exactly M, of exactly 1, 2, and so on? So, what are the possible total numbers of candies that you might create by using a subset of these boxes? And the question here is, if we are able to change the number of candies in one box, what is the maximum number of options that we can obtain after that? So we'd like to change the number of candies in one box so that the number of distinct orders we can serve increases as much as possible. And by change, I mean, this one, we can pick one number and change it to anything. In order for this number not to be too big, we assume that if there are multiple options, we'd like the number we change to be as small as possible, and within all solutions with that, we'd like the number we change it to 2 to be as small as possible. This is the one you know? Okay. Okay, so this is something we're gonna discuss tomorrow, but you might start thinking about it. I think it's maybe a little more fruitful to you to think a bit about this one before we start discussing it. If you just write can this be like 2010, you can find the task statement. You can also find the solution, which I don't really suggest you to read, because yeah, we're gonna do all of that tomorrow. And okay, I think now it's time for a break. So let's meet up like here in 10 minutes. I'm not sure.
maintain points and know the maximum angular coefficient of that.
You have some equations, right? There, like inequality. Because you have to find two numbers, right? So it's like you have a plane and those two numbers have to satisfy some inequality. One inequality tells you, okay, you have to be above some line, right? Then you have another one which you have to be above this line, above this line, and so on. So what you're interested in is an intersection of half planes, right? You have a half plane like this, and you want an intersection of this half plane and an intersection with this half plane. Right? Okay, so maybe. Oh, I see. Fine, great. Okay, so actually doesn't add one by one, but try some one step.
They are in increasing order. I am sure that the PL has the highest instead of
Não, eu não sei, eu não tô vendo nada. Aí você pode fechar. Chegou a pegar o Skype mais, você tá no Google, desenhando ao máximo.
Você faz isso ou você faz isso?
Digitaram lá.
Right, so now let's discuss the problems from yesterday. And I think we're gonna follow strange order. I suggest you it's just an alphabetic order. Starting from the very first one and then going further. We may skip some of them and also not say too much about the others, but I think we'll have time to discuss the most of them. So the first problem was the motorway. And that problem, we had some points in line. We were given their coordinates. And our task was to decide if it's possible to place n equally spaced additional points so that the blue and the green points alternate along the line. So the first, it starts with a green point and ends with a green one. So we were given the blue coordinates and we had to find the green ones. So let's denote this coordinate by y and this distance by x, and this would be a1, a2, and so on. All the way up to an. Right, it was possible that actually the green and the blue point were in the same spot. So if we rewrite it into inequalities, the constraint we have to satisfy is that I'll get it wrong if I don't copy it. Is that the beginning plus I times x had to be no more than ai, which is in turn less than y plus I plus 1 ai. So this one means that I point had to be before the blue one, but the next point has to be after this one, right? This exactly expresses the conditions that we have to satisfy here. So equivalently, we can say that, okay, from this we got that y is at most ai minus I times x, and from this we get that y is greater than x, ay minus I plus 1 x. Okay, so we have like a system of inequalities, and we have to find the two solutions. One solution which has the minimum possible x, and the other one that has the maximum possible value of x. Okay, so we're looking for pairs of numbers, x and y. So we can draw this thing in a plane. So these inequalities say that y has to be above some straight line. And there are more of them, so that y has to be also above some other straight line and another. So the points we are interested in are on this part of the plane. And on the other hand, we have the second type of inequality, which says that y has to be below some line. Y has to be below a line, say, which looks like this. And y has to be below the line looking like this, and some other lines. So altogether, if we draw all these lines, this is the region of the valid pairs x and y, right? So if we put those lower bounds together and the upper bounds together, we can observe that the lower bounds, they form a convex function, because it's a maximum this is a maximum of two linear functions. So lower bound look like this. Let's call this bound f1 of x. And the upper bounds, they look like this. Let's call this one f2 of x. Right? So we have to find something which is some points which are between a convex function and a concave function. So in order to do that, we consider the difference of those functions. f1x minus f2 of x. So f1 is convex, f2 is concave, but we take minus f2, so we also get a convex function. So in the end, we have f2 minus f1. So this is concave function minus convex function. What we get from this is a concave function. And this function here, it's 0 here, it's 0 here, it's negative here, it's positive here, and it's negative here, right? So what I want to really find is I want to find this point and this point in a function looking like this. So for that, I can use ternary search. So it's an algorithm that allows me to find the maximum of a concave function or the minimum of a convex function in a way very similar to binary search. So in binary search, before I say that. So we have those functions, but the question is, do we know what it looks like, right? So do we know what is the value of f2 of x minus f1 of x? Well, we can evaluate f2 of x in one point, like here, because when we consider some fixed point, we have those lower bounds, and for this point we have to find the maximum one, right? So we just iterate through all these equations. We have the value of here. We go through all these equations. We have the value fixed of x fixed. I mean, we're asking for a particular x, and well, if we know x, we can go through all the equations, and we know how big y has to be, right? And this is what happens here. Like to evaluate. In this point, we have to check how big y has to be, and this is just checking going through an equation. So we can evaluate this function and this one, so we also can evaluate this thing in a given point. So now we have a function which is concave, and we can evaluate it in every given point, and we want to find the places in which this function is 0. So the first step to do is that we find the maximum, and we find the maximum by doing ternary search. So like in binary search, we start with 2 points, one very far to the right, one very far to the left. And then, well, in binary search, we check some point right between them. But here, in the ternary search, we check for 2 points. And we check for the value. We divide this interval into 3 parts. We evaluate the function here, and we evaluate the function here. So now we have 2 candidate points, and what we do, we check which of them is lower, and we switch from this point to this one if this is the lower one, or from this one to this point if this is the lower, if this one is lower, and we'll keep shortening the interval this way, right? So in general, if we have some value here and a value here, we have 2 points. We evaluate the function in 2 places. If I get those 2 values, so if we have these 2 values, we can easily see that the maximum is somewhere somewhere here. So we get rid of this point and move here and now consider this interval. If on the other hand, we've got this situation, then we know that the maximum is somewhere in this interval when we move from here to here. And in every step, our interval is shorter by 1/3. So we can find the maximum value of the function, which is somewhere here. And then we can cut it into two pieces, and now in this interval we have to find the 0, and also in this interval we have to find the place where this function intersects the horizontal line. So this is a solution with ternary search followed by 2 binary searches. It's also possible to solve it with just binary searches, and I've seen that you did that, but I think that solution is maybe a bit more complex to be explained on the board. Any questions? We're writing that. Okay, so let's move on to the second one. The second one is what happened. What happened here is that we were given a grid graph from which edges were being deleted, and our task, well, after every deletion, we had to say if this graph decomposed into 2 connected components or not. So deleting edges, and after this deletion, the graph splits into 2 components. So the number of components increases, and then after this deletion, also the number of components increases. And after every deletion, I have to say whether it has increased or not. So whether I cut the last edge connecting 2 vertices. Now in this task, the format of the input was pretty strange. It was kind of encoded in a weird way. And do you know why that is the case? Yes. Yeah. So why so? Why can't we just list all the deletions in the input? Yeah. So if we knew that all the deletions in the very beginning, we could have read all the operations like we could have read all the deletion operations at the very beginning of our program, and then we could perform it all backwards, right? So we could delete all the edges, and then we'll go back in time. So we'll have edge deletions happening, but now we're going back in time, so we have the final graph here. And we're doing edge additions. And for every edge addition, we'll have to determine whether it connects 2 different components or not. And this is easy, right? This is just a undefined problem. So without this encoding, the problem would have a very simple solution, and that's why we encoded the input in some way. Okay. So how do we do the task when we cannot reverse task? Is there anyone who would like to share this solution? Okay. Share. Okay. Can you come here? Yeah.
Okay, so first of all, I'm gonna just write an example here. Okay, so I think that the first question that one has to ask to solve this problem is how can I see if two vertices are on different components, right? So in order to do that, what I first noticed is, suppose I have some vertex here. In order to this vertex be on like some different component, it had to be like this, right?
So, I mean,
Different region. Well, actually, it's not in different regions.
those edges have not been existent, right?
Yeah, but well, I'm gonna show here. Okay. So, okay, one way to do this is suppose I have this here, right? These edges here have been cut, right? So if I'm gonna cut this edge here, okay, if I'm gonna cut this edge here now, what I have to see is if suppose I'm gonna just build in a graph, just use the edge that have been cut, right? This edge here, then well, it's easy to see here that when I'm gonna just cut this edge here, that this vertex here, they are in the same component. So that's correct.
Yeah, that's what you're saying. Is that so you have a graph which contains the edges which are not here, right?
Yeah, which are not here. Okay, so if I see the component of this vertex and the component of this vertex here, they are the same, right? They are the same component. So it means that when I cut the edge of them, I'm gonna just create a new region, right? Right? Okay, so, well, that's not correct yet, because, well, suppose I cut all these edges here, but this vertex here and this vertex here, they are still connected, right? So, well, the last thing to note is to solve the problem is that you can just rebuild this graph here into the dual grid, right?
Yeah. So what you want to do is to build a dual graph, right?
Yeah, the dual graph. It's like
right on. That's pretty big. Okay. I think there was just one outside.
Okay, so suppose that I have cut these edges here. This. So this vertex here is not connected with all those vertices here, right? This one is not connected with this one, right? Okay, so look into the dual graph, I can see that if I connect the edges that have been cut into the dual graph, I will have this.
So for every edge which you do not have, you add the edge to the dual graph.
Yeah. This. Okay,
This is one vertex again, right? There's just one vertex in the other vertex.
Okay, so, well, I can see that this vertex here is not connected with this one. Okay, but suppose that I have this. That this edge here have been cut. Yeah. So, well, this vertex here is connected with this one. You know, you can use this path, right? Okay, so what I can see here is that suppose that I'm going to cut this edge, right? And I'm gonna check if this vertex here will be connected with this, actually this one,
Yeah.
right? Okay. So what is this to see is that if I get this edge here, that's gonna be cut in the dual graph. For now. Okay. So what I can see here is that this this vertex here and this one, they are the same component, right? The dual graph that I've made just using limited edge, right? So if they are in the same component, then if I'm gonna cut this edge between them, then I'm gonna create an enclosed region, right? A new region. And if I'm gonna create a new region, then this vertex here and this one, they will be in different region. So they won't be connected after I cut this edge, right? So, well, I just joined this one, they are just connected, just using profile, and I think that's the answer. Just using profile.
Yes. Thanks. Yeah, so that's exactly the way to go. Maybe this can be also expressed with some other approach. Namely, we can, like to convince ourselves that this works, we can use Euler's formula. Vertices minus edges plus faces equals the number of connected components plus 1. So since we want to maintain, after every edge deletion, we want to check if this increases by 1 or not, right? If the number of components increases. So when we delete an edge, the number of vertices stays the same. This changes by 1. We want to know what's the value of this guy. So we actually what we want to know is whether the number of faces has increased or not. This is what we need to know in order to check if the number of components has changed. The other thing, for others we know. So in order to do that, we simply have to maintain a find data structures on faces, right? So we'll have so right now every face is like an isolated vertex, and then we delete an edge and connect the faces, and the number of faces increases by 1. And again, here, if we delete that, the number of faces increases by 1. It decreases by 1, sorry. And so on. So we're connecting to those faces together. And then when we reach this point and delete this edge, the number of faces does not increase, right? And also we can see that, right? Because we have a union find data structure of the faces, and after every edge deletion, we connected two different connected components of this red graph, and with this deletion, the edge that we add does not connect distinct components. So after adding this edge, the number of red components does not change, and this is precisely the moment when the number of components in the black graph changes. So this is another approach for looking at this task. So here we had to use Euler's formula and duality techniques, and we got to the solution. Right, now very short solution for the task carpenter. In the task carpenter, we were given a grid with some black and white squares, and the question was, what is the biggest square that we can obtain, which looks like a chessboard and is created out of two right triangles? Now, I'm not going to tell you much about the solution here because I believe, so first of all, this is a task that was not meant to be solved. It's like an enormous coding work, and if you really want to practice coding, you might try this one, but I warn you, it's a serious job. But also, I think that this is one of the tasks such that when someone tells you the solution, you don't really get very much smarter because of that. So I don't think it's really fruitful to discuss the exact solution. Maybe I'll just give you a very high-level idea of what happens. So since we want to find two right triangles that are colored like a chessboard, we'll need to do some dynamic programming. So, well, those two triangles are definitely somewhere in this board, and you can observe that these two triangles that we have to cut out from this board are either separated by a vertical line, a horizontal line, or some line that goes like this or like this. And because of that, we're only going to use dynamic programming, so we'll have to do something like, well, for every horizontal line, what is the biggest triangle colored like a chessboard, which has, well, two variants, black or white square in its next to its right angle, and it's below this line. And then we do this for all lines. And then for every line going like this, we want to compute what is the biggest right triangle colored like a chessboard that's on this side of this line. And we do this for all possible lines and all possible sides. We find that the biggest triangles, and then we check all lines, and for a line, we want to take one triangle from one side and one triangle from the other side and merge them together. What you need to do for this dynamic programming to work, well, as a sub-problem, you need to solve something like given a board with black and white cells, find the biggest white square inside. So this is a pretty standard problem. I'm not going to discuss it now. Actually, it's not very difficult. It's going to be difficult, so you might be able to figure out the solution yourself. So this is a sub-problem here, and then we use this, combine this in like hundreds of ways in various dynamic programming approaches. The main difficulty that you face is that you need to be kind of smart in order to not to have too many special cases, too many different cases to consider. And then once you think of a solution, then you produce 200 plus lines of code, and you're done. Okay, that's it for this one. Let's leave it. So the next one is demonstrations. And in the past demonstrations, we're given a sequence of intervals, a set of intervals. And the question was, the task was to find two intervals such that when we delete them, from the set of intervals, the union of the remaining ones is as big or as small as possible, right? So we have to delete two intervals so that the union becomes as small as possible. So for that, we're going to calculate two values. One is di, the other is dij, and this one is total area or length covered only by interval I, and this is total length covered only by intervals I and j. So the numbers like 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. We just sort the starting points and the ending points of the intervals, and then we're going from left to right. And now here on this, at any point we just have a set of intervals that we're currently crossing, right? So we start here, we reach this point, we add interval 1 to our set, and we keep it. And then we add this length to d1, because this length is covered only by 1. And then we add interval 2. So we added the set, our set has now 2 intervals. We add this distance to D1, 2. And then we add a third interval, and now our set has 3 intervals, and since this part is covered by 3 intervals, we know that no matter what happens, it will be covered after deleting 2 intervals, right? Because we can delete those 2s, and there are 3 of them, so this thing will stay covered no matter what we do, and we do nothing here. And then 1 is erased. We have intervals 2 and 3 in the set, so we add this thing to D to 3. This part is covered by 2 and 3 also. And so on. This is not added anywhere, and then this is added to D to 3 again. This is not added anywhere. This is added to D 4, 5, and then nothing, and this is added to D 5, 6. This is added to D 6, 6, 7, 7, D 7, 8, and D 8. So we got these numbers computed, and now there are 2 options. So the 2 intervals that we delete, well, for the 2 intervals, the value Dij is 0 or it's not 0. Nothing else can happen. If this value is for the intervals we're looking for is not 0, well, we can simply go through all values Dij which are not non-zero. Well, we keep these numbers in a map because we don't want to have like an n by n array. So we have a map indexed by 2 numbers, which has the value of Dij, and we go through all non-zero values in this map, and so we have some candidate pairs Ij, and for a candidate pair we consider, well, if we delete Ij, we uncover this part, plus we uncover this, plus we uncover this, right? So all that was covered by Ij is now not covered. All covered only by I is not covered, and the same with j. So this is how much we uncover. And in the other case, if the Ij is 0 in the optimal solution, we check the value of the I plus, well, we just check the sum of 2 biggest values of the I and Dj. Some of you look like this makes no sense. If you want to ask some questions. Okay, so then if not, let's move on to the next one. The next one is exam, and I think every single team solved the exam, so let's discuss it. And then, I mean, I might be wrong, but if you haven't, then I think we could take, if you have some questions regarding that, let's maybe take it offline. And then the next one is speed cameras. And speed cameras, well, it's kind of a surprise because in the contest, the speed cameras was pretty easy, and I think lots of you thought it's not easy because nobody solved it in the beginning, but yeah, in this task you had to believe that it's actually not a very, well, it's not one of the most difficult that was to be done. So in our contest, this was easier than demonstrations, for example. I think it was the third easiest. So we had a tree with a number k, and the goal was to mark as many vertices as possible, so that on every simple path, at most k vertices were marked. So if k is equal to 3, we can mark this vertex, and this vertex, which is stupid, but then this path is already covered. So we cannot add any more vertices on any path that goes to these 3. And the goal was to not only to find yeah, the goal was to not only find the number of vertices we have to mark, but also to find the marked vertices. So how do we start? So the first observation that is, I believe, quite natural is that we can safely assume that all leaves are marked. I mean, if we mark a vertex, then it kind of steals us some further options. And so in a sense, marking a leaf is the safest thing we can do, because it doesn't reduce the number of further options that we have. So because of that, at the very beginning we can mark all leaves. And when we do that, then we can see that on every maximal path in the tree, we have marked exactly 2 vertices, right? Every maximal path goes from a leaf to a leaf. So this means that actually we can remove all the leaves. Increase k by 2, and we have the original problem again. So now we have the leaves, we have a tree, we can put at most k minus 2 vertices on every path, and we want to mark as many vertices as possible. So the algorithm is like, we repeat k over 2 times, mark all the leaves, and then delete all the leaves, and we keep repeating that. In the end, if k is odd, we might still have one vertex, one possible vertex to mark. So if k is 1, we just mark an arbitrary vertex anywhere, and it can be shown that this approach is optimal. Okay, the next one is marbles. Marbles, we had, what was that? These were marbles, or like balls and bins? Let me check. Oh yeah, there is an even number of marbles in the urn. I had this idea that urn is an object that's often used in combinatorics and probability, but nobody has seen it in real life. So we have marbles in the urn, and they have numbers on them, or digits, and they're A0 marbles with 0, A1 marbles with 1, and so on, up to A9 marbles with 9, and these numbers are huge. They're very big. The question is, can we split up the marbles into two urns? Some urn with marbles. Let's split it into 2 parts, so that the product of digits on these marbles and these numbers is the same. In other words, we can take the marbles labeled with 0, we split it into x0 and y0. So x0 marbles go to one urn, y0 to the other urn, and we want to what we want to have is that the product of xi is equal to the product of yi. Okay, so we can start by making some simple observations. Like we can take a look at 5s. Well, if we have some marbles with 5s, they have to be split evenly. Otherwise, one number will be divisible by by 5 to some power, and the other number would be divisible by 5 to a different power. So the products definitely will not be equal. And the same goes for 7s, and also 0s are kind of easy, because if we have just 1 0, then we're screwed. Like one product will be 0, the other won't be. If we have more than 1 0, then it's great, because we can just give 1 0 here, 1 0 here, and both products are 0. So these are some simple cases. But once we deal with that, there are like 6 or 7, I don't know. There are some numbers that oh, and I think ones are easy too, right? Oh, sorry. There is one more. Requirement I should mention. So not only do we want the products to be. This is not what I want. This makes no sense. Sorry. So this is not a product of it. So what I should write is product of. I want to multiply the numbers on the marbles. So I want to multiply I xi times here. I'd like to multiply I yi times. And another requirement I have is that the number of marbles in both terms are equal. Okay, that's how it should be. Sorry for the mix-up. So I'm multiplying the digits on the marbles. So I multiply I as many times and this thing, depending on the number of marbles I have. This is the right population. And I want the numbers of marbles in every urn to be the same. Okay, so anyway, in the end, we get into the situation when we have, like, when we dealt with maybe marbles of 3 types, and we have maybe 7 different types to deal with. So this task is about, let's say, it's about intuition. So when you start analyzing it or playing with it, or maybe you can see it immediately, maybe you have to analyze it. It kind of seems that it's not really, it doesn't really make sense to put, I don't know, to split the marbles really not evenly. So if we have 3s, then if we have like I don't know, lots of 3s, then you probably want to put a similar amount of 3s in one urn and a similar amount of 3s in the other urn. So it actually turns out that for every I, we can only consider divisions in which xi minus yi, so the number of marbles going to one urn and the number of marbles going to the other urn, are at most 6. This number has been determined experimentally. But what it means is that, well, it only makes sense to consider partitions that partition every type of marble kind of evenly. And because of that, we can just use some backtracking. So we consider all partitions that satisfy this requirement, and then check if one of these partitions is a good one, so that the product is equal, and of course the numbers of marbles are also equal. Now this of course gives you some backtracking approach. If you optimize it, there are lots of ways to optimize it. I think maybe using some of them, some easy ones, is necessary to get it accepted, but also it's possible to get a solution that runs like many times faster than the model one, and but this great speed up was not required. Okay, so this was a bit different type of a task. And I should say this was in this original where the task came from. This task was the second hardest. I mean, the hardest one was Carpenter, which was not solved by anyone, and this one was solved by 2 teams. So I'm really glad that we also had a team here that managed to solve this one. So now let's move to the next one, which is Hero. In the task Hero, we got a directed graph with some weighted edges, and there was an additional constraint that there are at most 10 edges. It's not visible. There are at most 10 edges out of every vertex. before is that if we have a vertex, the vertices were, sorry, for every vertex, we were forbidden to enter this vertex at some given times. So it was a directed graph with weights, and also for every vertex, let's draw maybe a timeline. For every vertex, there were some intervals of time in which it was forbidden to stand in this vertex. And the goal was to compute some shortest path from a given source to a given target vertex. Right. So what happens here? Well, we have to compute shortest paths, so this obviously would be some extension of the Dijkstra algorithm. So let us draw a vertex with the forbidden intervals, and another one. So the first thing that we do is that we split each vertex into multiple ones. So we split this is a vertex with some forbidden intervals. So we treat this thing as one vertex, this thing as another, and we treat all of these allowed intervals as separate vertices. Now, just like in a plain Dijkstra algorithm, for every interval like that, we want to compute a value dp, which is like the earliest time at which we may reach v. So I stress that it's per short interval. So for this interval, this time might be here, and this basically means that we can be in this vertex from here to, well, all time until it gets forbidden. And also for this interval, we might have some other value. Maybe in this vertex, we can be whenever we want. So, and so on. And our goal is to compute these values. Well, now how do we do that? We do it just like in a Dijkstra algorithm, but we need to use some clever data structures for performing relaxations. So say that we let's draw this line like this. Yeah, let's say that we are in this vertex, and we already know that we can reach this vertex at this time point. And there is an edge going from here to here, and it takes us that much time to go there. So what happens now? Well, we can reach this vertex at this point of time. We can reach this vertex at this point of time, because we can wait here all the time up to here, start walking in this time moment, and reach it exactly when it becomes available. And then the same goes for this one and this one, and probably we won't be able to go here because we can't wait long enough to be able to jump here. If we start walking up, then we reach, well, we'll try to enter the vertex when it's unavailable, so this is not possible. So what happens here is that in order to perform the relaxation, we just we have those intervals in some data structure. We find the earliest point at the first interval which we can enter, and then we keep checking if we can go to the next one, possibly the next one, and we keep going until either we're not allowed to wait anymore, or we get reached something that's not reachable. Now, this process is not correct, but it might be slow. To speed it up, we need one simple observation. So if we have a case like this and we start relaxing intervals, in the first interval, well, we are able to enter at some time point, but then for all following intervals, we are able to enter them once they become available, right? So like when they stop. So we have a data structure here which contains all intervals to be relaxed, and we update this one, and then update this one and remove it from a data structure. This guy doesn't have to be relaxed anymore. I mean, for this guy, we can enter as soon as it becomes available, and we don't have to check it anymore. And the same goes for this one and this one. And in the end, when we perform a relaxation, we relax one interval, well, possibly partially, and for other intervals, we relax them for good and like delete them. We won't be working with them again. So the time for going through the next intervals amortizes because as we're relaxing, we're also deleting them for good. And the total running time is you implement it well. It's like n plus the number of forbidden intervals times log n plus p. Okay, so 2 tasks to go. I think I'll also skip Janosik. I'm not sure. I have no idea how to pronounce it in English, but we say Janosik. Or the guy was in the title of J. So the next class is genetic engineering. And here we say that we get a number k and a string, and we say that a fragment is good if it looks like there is the same character k times, and then another block of equal characters, maybe another block with the same set of characters, and so on. So we have like groups of k consecutive characters all the same. We call this fragment good. And the task here was to find the longest good substring of a given string. And in case of a tie, if there are multiple, we have to select the solution which is lexicographically lowest. So it turns out that the second requirement is actually more difficult than the first one, because finding simply the longest good fragment is not so difficult. So in the very beginning, we're going to solve this task from back to front, and for every suffix that starts at position I, we'd like to compute what's the longest good fragment in a suffix starting at I. At position I. How do we do that? Well, we start here and we keep walking backwards, and we're counting the characters that we see. At some point, we get k occurrences of some character, and we know that we have found that here there is a fragment that is a substring consisting of k equal characters. So we cut, and we know that from now on we can have in this suffix there is a good fragment of like k. And then again, we keep walking further. Then we keep counting characters again, starting from 0. Once we see k occurrences of some character, we cut it, and we have a longer good fragment, and so on. So this is a greedy approach. Once we see k occurrences of one thing, we just enlarge the fragment, and we store the result in an array. I think it would be convenient to say that this is longest when we remember the number of blocks. Meaning, I keep 4, like there are 4 blocks here, so this fragment has length 4k. I mean, this is always a multiple of k. It would be convenient to do it this way. Okay, so this is the first part. So you can find the longest root fragment, and then now the second part is to find the lexicographically smallest one. And for that, we start from the beginning. And well, what happens? Since we want to get the lexicographically smallest fragment, we first want to assure that the first block has the smallest number possible. And we do everything to minimize the first block. And then once we do that, we try to minimize the second one and so on. So we proceed greedy. The only thing that we need to care about is that, well, we have to end this block early enough to be able to construct the maximum number of blocks. So if optimal solution consists of p blocks, then the first fragment, the first block has to end no later than at position I, such that if the first block reaches position I, then from here, so from dI plus 1, I'm still able to construct d minus 1 blocks. Right. So now the solution goes like, okay, I find how far can I go with the first block, and within this interval I also count the occurrences of every number, and I check and I find the lowest number which occurs at least 8 times, and this is my first block. And then the same problem is repeated. I go from here. I know how far can I go and find the lowest number which occurs at least 8 times. So this is it. There is just one technical issue that these arrays that you use for counting occurrences have to be zeroed efficiently. So if we are counting characters starting from here up to here, and then we decided in the end that the first block would be this guy. So now we'd like to continue our search from here. But our array for counting characters contains the count of all of these. So we can actually go through these characters and subtract them. I mean, this is a small technical issue. I think there are also other ways to deal with it. Anyway, the basic idea is that we first do dynamic programming and then retrieve the solution using this approach. Okay, now it's time for the last task from yesterday. The task, it was called blanket. So we said we were going to skip together. Yeah, we'll do that, and then correction. Okay, it's 11:30. I think it's good if we postpone this for tomorrow, because I think we're going to run overtime today. And for tomorrow, I have a little less planned, so I use the time tomorrow to discuss this one. So let me just deal with two things. So first one is something I promised to explain to you is that the task from the first day which did not work, the one about friends in a planar graph. So I thought about this one, and I think it just cannot be solved efficiently. What I had in mind is something similar, namely counting triangles in a planar graph. So the task I thought about is how to count sets of three vertices which are all connected to each other. I thought it's going to work the same, but apparently this one is easy and the other is not. So, like, how what you might want to do is think, given a planar graph, how to count all these vertices connected to each other in linear time, in line time. And be aware that this is not about counting triangular faces. A triangle is not the same as a triangular face because the graph might look like this. So this is a triangle, but it's not a face. Right? So it's not about counting faces, but about any vertices that are pairwise connected with edges. And the second thing is the plan for the afternoon. So in the afternoon, we'll have a 5-hour session, but this time it's going to be an individual session, and it's I want it to be a bit different than usually. So the afternoon session would not be a competition, but rather a problem-solving session. So the idea is that you get some tasks, and your goal is to solve as much as possible using any means possible. So you're free to discuss it with your friends, you're free to solve them in groups. The only requirement is that I want you to implement them yourself. And I'll be there, sometimes I'll be there walking and you can ask me questions. As I said, you can ask your friends for help with solving, debugging. So I think what makes sense is, of course, not to, like before even thinking for 5 minutes, asking for solutions, but try to do it in a way that you feel you learn the most. So maybe get a task, think about it for 10 or 15 minutes. If you don't move anywhere, ask for hints, and then try using those hints and so on. If you manage to solve one, also be generous. Ask if your friends need some help, and as I said, the goal is to get as many as possible solved. So you really have to find a good motivation and a balance between thinking and okay, at this point I should probably ask for some advice, because otherwise I wouldn't get this one solved. So this is what we do in the afternoon, and I hope it works fine. I'll be there. Well, I think maybe half of the time to answer your questions. Okay, and I think that's it. We meet in the labs 1 p.m.